Hello friends, in this video we are going to look at problem 2858, minimum edge reversals, so every node is reachable. This is the continuation for the video for problem 1466. The reason is that these two problems can be solved using the same idea. However, the problem here is a little bit harder, but still straightforward in a sense. So we need some extra trick to do this problem. So here we have n nodes labeled from 0 to n-1, and then we have a number of directed edges. So here ui and vi, meaning that there's an edge from ui pointing towards vi. So we can reverse the direction of an edge. So the goal is that we want to return an integer array answer, where answer I is the minimum number of edge reversals, so that it's possible to reach any other nodes starting from the node I through a sequence of directed edges, right? So if you look at example 1, so here if you want to reach 2, 1, and 3 from 0, you just need to reverse this edge. So that's a 1. So if we want to reach from 2 to all the other nodes, so because here is correct, so you don't need to make any reversals. If you want to reach all the other nodes from 1, so you need to reverse this direction, so you have a 1. So if we want to start from 3 and reach all the other nodes, you need to change this edge from 1 pointing to 3, and the edge from 2 pointing to 1. That's a 2 here. So that's basically the problem logic. So here, there's an important assumption, that is n is 10 to the power 5, right? So we know from problem 1466, so if we do traversal starting from a source, we can count the number of reversals needed, but we cannot do this for every single node. In other words, we cannot run DFS or BFS n times because it's too large, right? Because DFS and BFS will be O of n, right? Then if you run n times, it's n squared. But this number is 10 to the power 5. Then if you square it, it's 10 to the power 10. It's too large. So it cannot pass all the test cases. So that's the situation. So here we want to explain a solution based on one pass traversal. So you can use BFS and you can use DFS. So here there are several components or ingredients we want to emphasize. The first one is that we want to pretend the graph as bidirectional, but different from the solution for problem 1466. I'm going to use this treatment. If there's an edge from A pointing to B, then I want B in the neighbor of this A. But then I want negative A to be in the neighbor of B, meaning that there is an edge from A pointing to B rather than from the B pointing to A, right? So this is the one trick, because this way I can adjust the counting. And another thing is that if we do traversal, so let's say DFS or DFS, say, from a source, so we can get two pieces of information. So first is the cost, right? The cost I, meaning that the number of reversals we need. So in order to reach from source so to I, right? So this is the one. And also we can count the number of edges between the source and the node. So let's see depth I. So it's the number of edges from source to I. Actually, this one is symmetric, right? So which I mean that the number of edges from source to I and I to source is the same. But this one is not symmetric, right? Because of the directions, due to the edge directions. But with these two pieces of information, so we can get all our answer. We can get all our answer. So I'm going to use answer I to denote the cost from node I to all the other nodes. So here cost means the number of edge reversals. So that's the logic. So basically first we do a DFS. We get these two pieces of information, and then I'm going to explain the logic how to get all the answers for all the nodes. So that's what we plan to do. So we essentially using the idea of problem 1466, right? So now let's do the coding. First, I'm going to build the graph. So here, what I want to do, let's see, graph collections default dict. So I'm going to use, so we can use list, or we can use set. Is essentially the same thing in this problem setting, because this essentially it forms a tree, right? So essentially just one element or two. But here, if two, you have two elements. But it's at most n-1. But you can use set if you like. So can also use set. We can test that later. So then basically for AB in edges. So what we want to do is graph A. So we're going to add B. So this means that we have A pointing to B. And also I want to do this, B at negative A. So when we look at neighbor, if the neighbor is negative, it means that from the absolute value of this neighbor, that is absolute value of negative A, so then pointing to B. This help us distinguish the directions. So then what we are going to do, let me cost. So basically I initially 0. You can use list or you can use dictionary. Here I'm using dictionary for I in range n, right? Let me see. This is a cost from 0 to cost from 0 to node I. So depth, so let's I 0. So for I in range m. So this is the number of edges from 0 to I. Same as from I to 0 because it's because symmetry right here. So next we want to use a traversal to get to set these two pieces of information. So let me have a count variable. So this count variable is the same as in problem 1466. We are going to get the answer for node 0, right? So then we have a visited. Let's see. It's a 0, right? This is the source. And then I'm going to define if hyperfunction DFS. So from source. So from the source, because it's 0, right? The cost is, let's set it to be depth is 0, so no edges yet. And the cost is also set to be 0 at the very beginning. So I want to modify this count and also this two variable, cost and depth. So because this variable is immutable, so we want to non-local it first. You can also use class attribute to make this modification, right? And then what we want to do first, depth at the source is going to be D, and the cost at the source is going to be the initial value C. And then we are going to look at the neighbors. For neighbor in graph source. So notice that this neighbor can be positive, can be negative due to our special treatment, right? So first, if ABS neighbor, this is the genuine node name and not invisited, right? If invisited, we just continue, right? So if neighbor is less than 0, this means that we have a path. So from the ABS neighbor pointing to the source, because we want to go to from source to neighbor. So in this case, first we add this ABS neighbor, and then we do traversal. Then we do DFS. So this ABS neighbor. Then the depth will be for sure incremented by 1, right? Because essentially we counted the edges, but the cost is also incremented by 1 here, due to we need to reverse the direction because we want it to be from source to the neighbor. So this is one case. Another case will be the neighbor will be greater than 0. Notice that I'm starting from 0, then all the others will be with a sign, right? So this I do the same thing, visited add the node name, and then DFS, so from this node, and then the depth is incremented by 1, but the cost does not change because it's in the right direction. So that's the role of this DFS. So if I do DFS from 0, and then initially depth is 0, and then you will modify this count and also cost and depth. Let's print out that so that you have a feeling. Cost and depth and count, right? List has no attribute, so here let's use set. If you use list, so here we use append, right? So let's see. So notice that this count, so here I didn't increment the count. So here I need to, if the direction is reversed, so I need to increment the count. So here count incremented by 1. So now let's do that. So here count is 1, meaning that if we want from 0 to all the other nodes, we just need 1 reversal. So this is the matching here. And then let's count the depth. So from 0 to 2, as 1 edges, so that's 1. From 0 to 1, 2 edges. And from 0 to 3, 3 edges. That's right? So 0 is 0. And the cost, so from 0 to 2, the cost is 1. From 0 to 1, the cost is also 1. From 0 to 3, the cost is also 1. So with this information, so we are ready to prepare the return. This means that we get all the needed information to get the result. So I'm going to, let's see, answer will be 0 times n. So this is what we want to return, and answer 0 will be the count. So this is what we have already get. And then I want to explain how to get all the other answers. So for using this piece of information, cost and depth and the count, essentially answer 0. So let's do this. Here we can explain. So here, this answer I is the cost from I to all other nodes. So this all the other means exclusive except I, right? So then I'm going to first write down the solution and then explain it. So for I in range 1 to n, so we want to determine answer I. So answer I will be this. So depth I minus cost I. So this is one item. Then plus answer 0 minus cost I. So this will set the answer. Let's first test the correctness and then explain this line of code. So actually it contains a lot of information. Yeah, it passes one example. Let me comment out this print. Yeah, it passes all the cases. So now let's explain this line of code. So I can explain it here. So in order to determine answer I, so this by definition is a cost from I to all other nodes, right? So then basically this equals the cost I to 0 and plus cost 0 to all other nodes except I. So this is what we want to explain. So this equality is very easy to digest. And then the thing is that we want to claim so cost I, so I to 0, not so cost I to 0 equals this part. Depth I and minus cost I, and also cost 0 to all except I will be equal this part, answer 0 minus cost I. So this is the main logic for this problem. Let me first explain the here the first line, cost I. So cost I to 0, right? So it equals the number of edges between 0 and to I, or between 0 and I, or I and 0, the same. So minus the number of edges, because here I want to from I to 0, and then I want to minus the edges pointing towards 0, right? Pointing towards 0. Because for these edges, I don't need to make changes. But the first one, the number of edges between 0 and I is nothing but depth I by our definition. Then the second one, the number of edges pointing towards 0 is nothing but the cost of I, because by definition, cost of I is the cost, the edges pointing away from. So let's cost I is because we want cost I is the cost from 0 to I, right? So we want to reverse those pointing to 0. So this is exactly this one, right? So we get this part. So this is this line. Then because this depth I and the cost I we have already computed, so we get this first part. So now let's explain the second one, cost so 0 to all except I, right? So this will be cost 0 to all, right? So if we want to reach all the other nodes, then this is the cost. And then I want to minus the cost from 0 to I, right? That's so the first one is nothing but answer 0, right? And the second one, cost from 0 to I. So again here, right? That is cost I. So this is the second one. You have answer 0 minus cost I. So this is this line of code. Actually, it encoded a lot of information. So once you have this, so you get all the, once you do a traversal from the source 0, you get all the others for all the other answers, right? So actually this problem, you can start from all the other nodes. You don't need to start from 0. For example, you can from 1, right? So this is the one comment. Another comment is that here, if you use set, so here, let's see, dict, if you use set, you can use add here. So let's test that. Right. So let's also test if I use other nodes. Let's see. So if you use other node, for example, here I use I, and we need to change here, right? No, answer I, and then we need to also redefine this, but we will not do that. But the idea is essentially hopefully the same. So with that said, I guess that's basically about it for the current problem. This problem compared with this problem a little bit harder. So two tricks. One is here I'm using negative numbers to distinguish direction. Another one is that we need to digest this line of code in order to get the full logic. So with that said, I guess that's about it for the current problem. Thank you.